I'll move on to the second bit, which is about the build the best practices with Python containers. And now I'm asking a bit of a question for the last time. So there is one more bit, which is just some review of some best practices, and then I'm gonna start with the hands-on on my terminal. So the first thing that I wanted to point out today is about base images. So as we saw in any Docker file, we need to start from some point from somewhere to build our container, and you use the from instruction to achieve that. So picking the right base image is important. It can save you a lot of time and make your container better. I mean, in principle, you could always start from a plain operating system image such as Ubuntu, Debian, CentOS, or whatever. But there are much more valuable base images available in Docker Hub. So here I'm just mentioning the ones that I'm going to use today, and I believe might be useful for you as well. So there is an official Python repository on Docker Hub. And so we are going to use today Python 3.8, which is the latest stable Python release. There are two flavors there, 3.8 and 3.8-slim. One is about 1 gig, one is about 100 megabytes. And the reason is that in the first one, there is plenty of additional packages that apparently are typically useful in a number of workflows. I would start from the slim one though, because that way you don't unnecessarily grow the size of your container with stuff that you won't use in production. And that way you also reduces the chances of clashing packages, even with packages that you don't need at all in your final image. So I would recommend always starting from the slim one. And you'll see that in a lot of other images in this list, there is the same opportunity. So there are official mini conda images for conda fans. There's a mini conda one with just conda, and the anaconda one with the full anaconda stack. I would go with the mini conda one. You might or might not know that Intel provides an optimized Python framework with improved performance for scientific computing. So also in the form of a container. So it's Intel Python / Intel Python 3 core or Python 3 full. And again, I would go with the core one. And we're going to use that one later. Pawsey provides some base images for which already ship with MPI libraries. And again, this can be useful if you need to install and run MPI-enabled code in your container. So there is the mpich base, which is currently fully supported on all of our systems. So that's the one we normally recommend. And I'm also developing some OpenMPI support on the clusters right now. So if you go a look in this Docker Hub repo, you will also find some OpenMPI base images that are still not completely supported on the clusters. NVIDIA provides some CUDA-enabled base images, 3 flavors based on time and devel. So the base one is only what is required in terms of libraries to run, compile the CUDA code. Runtime has some extra libraries if you need them in your code, such as QBLAS, QFFT, and so on. Devel has got the full CUDA software development kit, so compilers, debuggers, profilers, and so on. We're going to use this one in an example later on, because it turns out that Numba needs a full SDK to run. We're not using it today, but also be aware that there are some Jupyter Blast images if you use Jupyter notebooks a lot. In this page, I've put, for your convenience, the links to the Docker pages where you can find these images. So for instance, Pawsey and pitch one will open up this way. And you can see all of the tags that are available. Couple of Ubuntu flavors. But crucially, I've also added the links to the Docker files. And the reason I've done that is that reading the Docker files of these base images can be quite useful. First thing, you get to know how the maintainers of those base images have built the image, so you know exactly what you're using. But second, you can also get useful hints on how to optimally use them, and also how to improve the way you develop your own images, because you might learn some clever ways of configuring stuff in containers. So we're going to have a look at a couple of Docker files for these base images later on. So picking the right one can really save you a lot of time and improve your image development process. And very last scrolling bit, let me mention some building best practices in general before we try and apply them in specific examples with you. So first tip is to try, I mean, this is not for performance or to get it working, but it's just to be optimal in the size of the final image. So it says try and condensate commands into few run instructions. And that's because, as I said before, a Docker image is layered, and it happens that each and every instruction in the Dockerfile creates a new layer. And the key feature of these layers is that it corresponds to a snapshot in the image. So every time you create a new layer, there is a full snapshot in the image of that, of the content of the layer. And the snapshot takes disk space. So for instance, if you have a run command that creates some files and the next command deletes those files, space for those files will still be taken by the image, because in one of the layers, those files are present. So you want to strike the right balance between not having too many run commands, which would overgrow the size of the image, and not having just one, because if you have only one, it would be very hard to read. And also, if you need to debug and develop your image a lot, it also means that you're basically hindered from benefiting from the caching feature of Docker. Because if you only have one image, there's no way you can exploit the cache from other layers. And so the optimal is actually in this section, in this paragraph. So the wise thing is to group together in the same run instruction commands that relate to the same component of the installation. So say you're installing the compilers, you have one run command where you install the compilers, configure them if you need, clean anything you need to clean, and that's it. The next run will compile your code, the next one will pip install something, and so on. There's no way you can reduce the size of your container more with this approach, because if the components are independent, it means that the different layers don't have anything in common. So there's no way you can save extra space that way. As I said, this is not compulsory to do. You can just, if it's easier, you can just keep on using the number of runs you're familiar with and confident with. But it's maybe something to aim for as you grow experience in building Docker files, in building images. And also remember that this space-saving tip only applies to the Docker format of images, because Singularity squashes everything into a single big file anyway. So all of the caching is DOS, all of the layering is DOS. So this is basically just to save space when you store the Docker image on the registry, which actually means saving time when you download the image. Second tip, clean the installation process. And this is really a way to save space as far as you embed the cleaning commands in the same run command where you install your stuff. And so just to show you an example, if you use aptiget to install something, here I'm just installing some compiler tools and so on. In the same run, you might want to have some cleaning aptiget commands like clean and purge, and even manually cleaning some system directories which might end up being filled by install time files. Similar thing, if you are building something your own, you might want to create a dedicated directory for the build. So a directory where you download your source code, make install, or anyway copy your final binaries and required libraries somewhere else in the directory tree of the container, and then wipe the entire build directory. That way you can save space. Third tip, okay, this is, we're gonna see examples of this, but so this is kind of a useful Docker feature. So you can abstract away versioning of the packages with some Docker syntax. So there is a Dockerfile instruction called arg, which allows you to define a variable. In this case, it's just tool version. And the nice thing is that any variable defined with arg can be overwritten and redefined at build time. So here you see a command to build a container. So Docker build, we're calling the container tool, and then we're using the build arg flag of Docker build to override tool version to version 3. And this can be handy if you need to handle multiple versions of the same package, and if you need then containers with the different versions, because you can just maintain a single Docker file and just build images with different versions by playing with this build arg feature. Of course, you need to ensure that the commands that perform the build in the Docker file are consistent with using the variable, otherwise it won't work. But this basically corresponds when you use a bash script to install stuff and you abstract away versioning using variables, using bash variables. Almost finished. So containers are mostly about runtime reproducibility. So you build your container image, you run it anywhere, it will yield the same result because it's the same installation. But if you maintain container images a lot, you might be interested also in build reproducibility, which means I have a Docker file and I use it to rebuild what should be in principle the same image in different times a long time. Am I still getting the same final image as a result or not? This might be a good question, as I said, if you build a lot of images, right? So just some tips to get there. You should rely on explicit versionings of the relevant packages in your image as much as you can, because that way you avoid just letting the package manager or whatever other machinery you're using to pick the latest version or the default version. If you want to enforce a given version of a key package in your container, just be explicit with the versions. We're going to see some examples with Python and conda. This basically boils down in the Python context to using requirements file a lot. And but it also corresponds to avoid using, say, aptiget upgrade in your container or pip install upgrade or something, or things like this, because all of these commands are normally useful in a Linux installation to be to the latest version. But if you do that in a Docker file, it means that if you repeat the build in 6 months from now, you will most certainly get a different final image. So the way you enforce the latest version in a Docker file is by actually changing, say, the explicit version of the operating system or of the packages that you need. And for the same reason, avoid using the latest tag for your base image. Just grab a version image. Last one I want to mention, just a couple of possibly useful environment variables that you might want to define in your container. So this one, I found it by chance one day, and it can be quite useful. So it relates to aptiget in Ubuntu and Debian, sometimes prompting you for information during the installation process of a package. Well, of course, you can't provide that information when you build a Docker image because you're not interactive. It's just Docker performing the build. So you can actually tell to Debian and Ubuntu not to ask you questions and just go for the default answers you might have. And you do that by defining this variable Debian frontend to non-interactive. So this can be useful with a lot of apt installations. By the way, I was lazy enough not to include this practice in the examples later on, so apologies for that. And this one can also be useful. It's actually also implemented in the Python and conda based images. So it's about localization, language localization and character sets. So it's a good and wise thing to define the language set in your Docker image to avoid unintended behaviors or even weird behaviors, both at build and runtime for your container. The typical choice seems to be, to me, UTF-8. So this is the one I'm suggesting here. There might be cases where this is not the best one. There might be a better one, but my suggestion is to always define this in the container to avoid issues. And I leave the other ones out because they're not that crucial. And I'm now going to start with some hands-on examples, which basically apply the practices I just showed you, just to see what happens for real. So I'm maybe going to start with the Ubuntu one and stop or if you have any questions, and then I move on to the Python example. So let me go back to my terminal. So here I have a copy of the Git repo that is behind this workshop. So just to ensure I'm at the latest version. And I'm running in a Nimbus instance, which has both Singularity and Docker installed. Okay. So there is a directory called exercises here, and let me start from the Ubuntu case. So here it's a very simple case. Suppose it's almost dummy, but it's actually something you're going to do in some of your containers. It's just installing some build and developer tools. So build essential, which includes the GCC and G++ compiler, make, autoconf, and so on. Fortran compiler, Git, and wget. Plain and easy so that we can run through it quite quickly. Let's build the first image and then start from there. So let's call it, yeah, U1 it's Ubuntu. So this should be hopefully quite quick. Right, more packages than I remembered. Should be almost there. All right. Okay. So the build was successful. The tag U1 latest was created. In a real production environment, I would use an explicit tag for my image, because that's again a best practice to enforce reproducibility of the runtime. You want to have versions that specify the container you're using. Here, I'm just playing with these Docker files, but actually to be really picky, let's build one more tag which uses the tag. So U like Ubuntu :1. So that's possibly better. All right. So we can see that the image was created also by listing all of the images in my instance with Docker images. And here it is, 318 megabytes Ubuntu image with the build tools inside it. What next? So let's start and have a look at how we can clean the installation with aptiget to reclaim some disk space for the Docker image. So let's have a look at the Dockerfile.2. And you see that I have just added a aptiget clean all and the removal of some files from an apt directory. And I've done it as a separate run command. So let's build the image from this second Docker file, which is basically just with these 2 extra lines compared to the first one. So let's go docker build, U2, Dockerfile 2. You see it's very quick because I'm exploiting Docker layer caching. So the first 2 instructions in the Docker file were the same as the previous Docker file. So the layers are just reused from Docker cache. And the only extra thing is the cleaning process. So are we gaining anything in space here? Docker images. So U2 is exactly the same size as U1, 369, 379, 379. And that's actually because of the layer behavior I was mentioning before. So I'm doing the cleaning, but I'm doing it the wrong way. So I'm doing it as a separate layer. So Docker still has to snapshot the content of the previous run command in the image. So there is no gain in saying, hey, delete some files. If you really want to delete some file, we have to embed the cleaning command within the same run instruction in the Dockerfile. And so you see that here, the aptiget clean and the removal of files is embedded within the same run. And so it's different lines, but you see it's the same run instruction. And here I'm just using new lining and double ampersand to break a single command down in multiple lines just for readability. But it's actually the very same. It's all in a single execution line, bash in Docker wise. So now if I build the container from here, let's call it U3. So now I can't exploit the cache because there is no such layer in the cache which runs that new longer command. And so that's why it's redoing all of the apt installation all over again. But then we're going to see at the end whether we're gaining any space for the images or not. Should be almost there. Here we go. Let's have a look with Docker images. And you see now that U3 is 350 megabytes. So we saved about 10% of the image size by cleaning the image the right way. This is not much, but this type of cleaning can be really powerful, especially when you are building from source. So if you get rid of the source and the object files at the end of the build, you can really save a lot. This was just an example for you. So what do we have here? We have one more Dockerfile in this Ubuntu example. And this one is about explicit versioning. So you might or might not need this. It depends on the type of image you're building. So in the case, for instance, of the Pawsey MPI-based images we provide, we use these actually because we want to provide support for a couple of Ubuntu versions. And so this is exactly what we're doing. So we are abstracting away the Ubuntu version by using arg and defining an OS version variable with 1804 as the default. And then we use OS version here. And so this means that with this Dockerfile 4, we could do something like, let me just clear the screen, Docker build. Let's call it U4 2004. We're using Dockerfile 4, and then we are using the build arg flag, and we are redefining OS version to 2004. So in this way, we can reuse the same Dockerfile, but support different versions of whatever we want to keep versioned in the actual Dockerfile. In this way, in this case, it's the operating system version.
I have a question for you, Margot, which would be useful for the...
Yeah, perfect. Yeah, as we wait for...
So I'm just trying randomly doing a Debian Buster build.
Yeah.
I just grab a hodgepodge of packages and it failed because some of the packages aren't listed, right?
Okay.
So that chose the wrong name, it just complains. Or if you choose one which normally has maybe some issues being installed, what happens then? So I try to install, let's say, RStudio. And I type in Debian, do a wget and try to install from an actual Debian package that I grab. And it fails, let's say. What happens? What does Docker do at that point? Can you recover from it?
Yeah. So what happens when you have a failure along the build? Let me just grab this other one. When a build fails, you still benefit. So say we are failing on this run command. What we gain from Docker is all of the previous layers are still cached in the system. So all of the unfailed, all of the successful layers have been created anyway. So if you need to debug this specific run command, this specific layer in the image, that's when caching becomes useful, because you don't have to rebuild everything over and over. If all you need to do is just amend this run command, every time you rebuild, you will still just reuse the previous layers. So that's when Docker can be quite useful at the development stage of the build.
Yeah, I was going to say that's something that you might find particularly useful, especially if you're not certain what packages you need, where the versions are there. Normally, maybe you cache everything you can, because you could do the run aptiget and grab all the sort of base packages you know you need, and then clean, and the same run command. And the next run command could be, well, I don't know, I need maybe some other packages if you're kind of play with it, because then you've got a basis to start from. It's the same thing, you'll always grab, like Ubuntu will be there, because you're going from Ubuntu, so it'll cache that automatically, and then it'll add some more stuff on top of it if you can.
Yeah, that's a great comment, actually. So, for instance, with aptiget, I've done it sometimes. So I have a run command, which is kind of standard with all of the build tools.
Yeah.
For the one image where I need the package X, I might add package X in this list, but as Pascal said, it's not the wisest choice in terms of caching. So if it is really a specific package, one more that you need compared to a standard list that you typically use for other images, you might just want to trade maybe what is really a minimum amount of space and just create an extra layer just with that package. And this can save you a lot of time. It's one more layer, but it can save you a lot of time at the development stage. Yeah. And it's a trade-off, of course. Sometimes you might see that if that saves you a day or even hours, it really can be a useful thing to do. I think my worst nightmare is TensorFlow. So if you ever need to build TensorFlow your own, try to avoid that as hell. There are a lot of ready containers with that, and they're really a blessing, because TensorFlow literally takes around 1 day to build, and when you find an error in the middle, that's when you start to benefit from from layer caching with Docker. Thanks, Pascal. And just to show you the result of this last build with Ubuntu 20.04 just achieved with the build argument flag. So you can see the U4 is a different size compared to the previous images. So this might kind of provide a hint that there's something different in there, but let's have a look for real. So Docker run U3 cat. So let's see the version of the operating system by having a look at this file etc.os release in the container. So for U3, it's Ubuntu 18.04. Here we go. For U4, for this other one that we built using that versioning flag, it's 20.04. So we did it. Okay, I'll just stop for a couple of minutes now. In case you have any questions up to this point before I go ahead with Python examples.
Margot, it's us questioning things. So in terms of the size, so when executing the container, does it matter really? Or it is more for managing your space in your building environment? Because I have run out of space many times in my building environment, that's for sure. And that should be an advantage. But is there any advantage when executing the container?
Not really. So it's really mostly for build time. It actually also only for Docker images. So as we have a very small minor break, let's convert in Singularity format a couple of images with Singularity pool. So I can retrieve images from the local Docker repo with Singularity pool Docker daemon. So this will look for images locally. So let me convert U2, which was the one which was not really cleaning stuff. So it was cleaning, but in a separate layer. And then I'm also going to convert U3, and we'll see what happens with the sizes when we go in singularity format. So spoiler alert, yeah, it really, the only context where this cleaning matters is basically the size of the image. And the additional care with layering really just matters for Docker, because as I said, singularity squashes everything together, and we're gonna see this in a minute or so. Meanwhile, I apologize to the audience because I didn't say this explicitly. So if you guys want to run this with me live, take the chance in this couple of minutes to open a terminal where you have Docker installed, and git clone this repo, and let me share with you the URL. So I'm gonna put this one both in the Slack channel. So if you git clone that, you will get these materials, and also just for redundancy, also in the Zoom chat. Here we go. So apologies for forgetting that, but the meat is coming. So as you saw, you just missed the Ubuntu bit if you were not set up. And so you can basically do in your Docker enabled machine, if you go git clone and then paste the content, the link that I put in the chat, this will basically clone this containers repo, and then just inside the exercises directory there. But as I have now built the singularity images for, so this is U2 and U3, and they're both 120 megabytes, so same size. Just for reference, U2 and U3 here, so they are the ones where I'm cleaning in a separate layer, or I'm cleaning in the same layer. So there is a difference in Docker, but there is no difference in singularity. And that's because singularity squashes everything together. And you also see that the singularity image is smaller than the Docker one. It's about a third. And this is the typical ratio, as far as I can tell. And that's because, right, because we are squashing everything in a single file. So there is no duplication at all in a singularity image. And so, yeah, you even, when you ship singularity images, you're also getting something in terms of space. This is, however, the last bit in your image development process, because once you're in singularity, I mean, when you need to rebuild a Docker image from a Docker file, you need to be in the Docker format, right? So you just get to the singularity format when you're ready to ship the image for production on the HPC system. So let me know if any of you wants to run the hands-on with me from now, and but is having trouble in setting up, let me know. Otherwise, I will go ahead shortly.
I was just going to mention as well that it's a good idea to be careful and not to download too many packages you don't need, because the Docker images can get quite large. So I just thought I'd give it a try and grab rcram base. So that's everything that's R, Clang, and GCC compilers. And so my image is 1.2 gigs, right? Yeah. So to give you a reference of the relative like 300 something megs that Marco just built. Grabbing just essentially minimum stuff. So if you do the same thing with Python and so on, you want to make sure that you grab only what you need.
Yeah.
So if you don't need everything, don't grab everything. And be, as I said, be specific. If you just need Fortran, grab Fortran. If you needed Python, grab Python. Don't try to grab everything, because it just ends up being quite large. And even the singularity image will also be larger. So,
so as you mentioned R, you can see in my instance I've got some R images. And so you see that this Rocker RVer is just a plain R installation of the framework with no extra packages and nothing else. It's 600 megabytes. If you add RStudio, it grows to 1.5 gigs. If you add the tidyverse package on top of RStudio, it's 2.2 gigs. And so, yeah, I think this kind of demonstrates what Pascal said. And it's even, I'm not sure how much R you're using. I'm personally a Python fan, so I tend to put more focus and highlight on Python images, but still there is a lot of art happening in scientific computing. Anyway, in your case, what some of you might need to use is CUDA, and so NVIDIA CUDA base. So just the couple of libraries for running a CUDA compiled code with no need for any CUDA libraries such as cuBLAS and so on, 100 megabytes. And this is based on Debian. And actually, this is based on Debian. CUDA runtime, so with the extra CUDA performance libraries, 1.3 gigabytes. And then there is CUDA Devel, which is the full SDK, 3 gigs. So yeah, I mean, you should really, even when you choose the base image, you should be aware that you can grow the size quite easily. With CUDA, there is a trick that I'm not covering today, explicit in the tutorial, which is multi-stage builds. So when you need the CUDA SDK just because you need the compiler, but then you don't need anything at runtime, so then there is no need for carrying over these 3 gigs in your final image. So there are ways of writing the Dockerfile so that you can basically define 2 base images. One base image for the compile part of the Dockerfile, which will normally be the larger one with lots of extra build tools, and then define a second runtime image, which is much smaller, that will let you save lots of space for the final image. I'm not covering it because it would have grown the length of this tutorial quite a lot. And in principle, it's a great thing, but in practice, you don't really require that often. Just be aware that there is a way to build images in a multi-stage mode. And if you really need to squeeze some disk space out of your final image. And yeah, with that being said, if there are no further questions, I'm gonna go ahead with the Python examples. So the first one, so now the goal, I'm trying to please you guys here. So my main package that I'm using as an example is astropy. So the goal in this example, in the following one, which will be with conda, is just to install astropy in a container. And we're going to start and see that using Python and pip first. So, and similar to the Ubuntu example, we're just starting from the simplest Dockerfile that you can imagine that does the job, and then improve it over and over. So this is the first one. So as I said, there is this nice Python 3.x-slim images available on Docker Hub, and that's the one I'm using. This comes with Python, pip, and really not much more. So if you want to install astropy in the container, you just set an extra run instruction with pip install astropy, and that's it. This is just me liking to always have the default container command set to bash. And the Python image would set it to the Python console instead. So this is just my personal preference. And to convince you of this little detail, as I run the build, so Docker build Python, so let's call it p:1 with Dockerfile 1. As the build runs, let me show you the Dockerfile of this Python-based image. So here I'm back to the tutorial web page, Python Dockerfile. pretty large Dockerfile. It's about 150 lines, I think. So it does a lot of stuff. Hopefully it does it good. So it starts from Debian bust Slim. So a bit, Debian ships various sizes of base images. Again, the non-slim one has stuff that is usually not required. So Python does what I think is the right thing and starting from the slim version. Adding some path, setting the lang locally, as I showed you in my best practices. And then it does lots of stuff. I don't want to comment on all of these. So it installs a lot of apti dependencies for in building Python. One nice thing, which is notable, so it builds Python from source, and it's doing it in these lines here, and not how in the configure step, it's enabling optimizations of the build. So this is a good reason, for instance, for using this Python-based image and not just aptigetting Python with the package manager, because in that way we just get a binary version of Python. Here you are building with a build optimization, so you most likely will end up with a faster Python framework in the container. So that's the right way. So this is the Python installation. This is just creating a bunch of symbolic links. This is installing pip, right? Python get pip, here we go. And then the last thing it does, it sets the default command is Python 3. As I said, I mean, there is no big deal here, it's just me. And just to show you what it does mean in case you've missed that. So that default command means that when you run Docker with that image, if you do that without, sorry, slim. If you do that without any commands, they want to be interactive, it will open the Python console. And I just prefer instead, and this is what I did in my P1 image, I just prefer to have the bash shell by default. That's all. That's not the only reason why I added a command instruction in the Dockerfile. So we have our first Python container with astropy inside, right? And we can see in the image list, it's 228 megabytes large. Notably, let's just have a look. You maybe you all know already because you might be using astropy a lot. I just discovered it last week, by the way, that astropy has just a couple of dependencies, actually just one, which is numpy. And actually, this is why I picked it for this example, because it's good. I wanted to have a package installation which had at least one dependency. So we installed basically astropy 401 and numpy 119 in the container. How can we clean the pip installation and save some space? Dockerfile 2. There is a nice no cache dir flag for pip that will save you some space because it will disable saving the source will files in the pip directory. So if we build, if we install astropy with pip this way, so docker build, I'm gonna get lazy, Dockerfile 2, and we're gonna call the image p2. He has to do it again because he can't use layer caching because it's a new layer. There's a new instruction there. Let's have a look at the size, and we're saving 20 megabytes, about 10%. Again, not much, but in larger container images, that might be more. Okay, so that's how you clean a pip installation. Now about versioning. So the simplest way we can imagine is just to define an astro version inside the Dockerfile, as we did with the Ubuntu version example. So astro version, and then being explicit here, right? Astropy equal astro version. That way, if we want to install, as in this case, 323 rather than 401, we can just play with the build arg flag of Docker. So we can have a Docker build p3 323, right? And that would be 1. But now if I decide I want 401, I just add that build arg flag. And here we go. So same Dockerfile, I can control different versions of the package. And I think it's complaining because I picked the wrong one. It's the beauty of the live session, because the right name is actually 401.post1. So let's try it again with the right version specification. And here we go. Okay, so versioning 101. However, we noticed just earlier on that astropy also depends on numpy. So with the way we implemented versioning in this Dockerfile, we only control the astropy version. And I'd say with Python packages, either pip or conda, this can be quite dangerous because we might want to have granular control of all of the versions of the packages we're installing. So, and that's when it can be actually useful to switch to a way of working with pip where we use requirements files. And so this is what we're gonna do. We're gonna have a requirements.in, which is just the specification of what we want in the container. We want astropy 323. But then we're gonna use a way to convert this minimum specification that we want into a more detailed concretization of all of the packages and versions that requirement corresponds to. And we can do that in a couple of ways, which are both documented in the material. So one is with pip freeze, and involves basically going for a dry run of pip, so that you install what you want and you extract the information on the full list of packages from there. That's documented in the web page of the tutorial. I can show you, but I will just keep that in the interest of time. So it's here, pip freeze. The other way is by using by installing in the host a pip tool, so a Python tool called pip tools. Okay, it should be already installed, but so this is in the host. I'm just ensuring it's there, because once you install pip tools, you can do interesting things. Pip tools provide a pip compile command, and if you go pip compile requirements.in, it will produce the full list of packages and versions that correspond to your request. And so say the way I want it to be done, this is just to comply with the Dockerfile I've written. I want to write this output in a file called requirements for whatever, 3 September, that's when I wrote the tutorial. You can use a -o flag to specify the output file of the pip compile command. And so you see that now the file has been updated and the content is exactly the same of what was shown in the screen. So there is a comment line saying how the file was generated. And then there is the list of all of the packages and versions. And then you can modify the Dockerfile to use that. So yeah, I'm just defining an argument variable to specify the requirements file I'm using. That way, say, if I really need to update that list of packages later on, I can create a new requirements.txt with a different date or a different name, whatever. And I can use the build argument flag to build different containers. Whereas normally for a given container, the initial requirements won't change, right? or if they do change, you can track that with variables as well if you wish to. Here we're learning how to use a new Dockerfile instruction, which is add. Add allows you to copy some host files in the container. And here I'm copying requirements.in and the requirement file in the container in the root directory. And I'm copying the first one with the same name and the second one with a standard name just for ease of use later on. And remember, this is the one, the second one, requirements.txt, is the one involved with the full specification. So in my pip installation, in the next line, pip no-cache-dir install, I now add the flag -r requirements.txt. So I'm now telling pip, install the packages that are in that list. And to enforce full reproducibility, I'm also adding this flag no-deps that tells pip, if any of those packages need something more, don't install it. Just install all and only the packages that are in that list. This is dangerous because if the list is incomplete, you will get a broken container. But with the protocol I showed you using pip tools, pip compile, that won't happen because the list in that file is complete. That was generated by pip. So we don't need another check here that might just end up with untracked, unversioned packages in the container. We just want exactly the content of this requirements file. That way, if we run the Docker build 6 months from now, we're going to get the same output Docker image. And if we really want to update the list of packages in the container, we need to manually and forcibly update the requirements file. Right? So this is a good way to enforce build reproducibility with pip in Python. Okay, so I think this is all for the Python the pip example. There is one more Dockerfile just because I'm showing the pip freeze way and the pip tools way. You can have a look at that in the workshop later on. Now, it's quite late, so in the interest of time, I'm gonna go ahead with the conda example and just read through it here in the web page. Also because conda installations tend to be a bit more lengthy than pip ones. So let's install astropy, but with conda now, in case you really love using conda. So now we're gonna start from a different base image, so the Continuum.io official mini conda image. And you can see in this starting Dockerfile, I'm using the naive versioning, which just uses which just sets the explicit version for astropy itself. The final size of the image is 1.6 gigabytes. How to clean a conda installation? The answer is in the second iteration of the Dockerfile. Well, in the same run instruction of conda install, you just add conda clean at the end. With -a means all, -y means go for it. It's just a confirmation, an automatic confirmation. If you do that, you get a 14% reduction with this specific example of astropy to 1.37 gigabyte, down from 1.6. So conda clean as a final command to clean up conda installation. For build reproducibility, I just wanted to note here that I tried to use no update deps in the conda install command. Just to tell conda, please do not update the content of the base mini conda installation. This is just, I mean, to be reproducible, again, 6 months from now. Well, it turns out that it doesn't work. So even if you say no update deps, it will still update conda and the other bunch of stuff that is in that base image, which is a bit disappointing to me, but there's a workaround to that.
Quick question regarding that.
Yeah.
Have you tried different mini conda versions to see if it got?
No, I haven't.
Okay.
Good point. It might be a bug. Yeah.
Because I mean, it could be that one of the later condas they introduced a bug so that it doesn't get respected. It's odd to have that command be there and not be respected. So. Yeah. But yeah, if people are trying with their various versions of condas that they've got installed, they can try to see if that version works out okay. If that command is respected.
Thanks, Pascal. So next step, how can we improve build reproducibility? So here we just versioned astropy. If we perform the build, we would have seen that conda installs over 30 packages to support astropy. So how can we version control those? So there is no pip tools with conda. So what we're gonna do is the equivalent of pip freeze, which is conda export. And to achieve that, we're gonna do something that you often need to do when you develop Docker images, which is to live debug and live develop your installation. And so what you do, you can prepare a requirements.in file similar to what we did with pip, with the astropy version we want. And then we're gonna go for a dry run. So we basically just open an interactive session of the base mini conda image we use in our Dockerfile. So Docker run, this is just a flag to keep the Docker environment clean from the container you have run and completed, just to save some caching space in your system, so not really important. This is important, this is to get the interactive session, the interactive bash session in your container. And this is just to bind mount the local directory because I need to read the requirements file from there. So I'm mounting the pwd, current path, and I'm calling it dash data in the container just to be standard. And then I tell Docker, set the working year to dash data. So that way, when the bash session starts, it starts in that directory, which maps to the host current directory. So if you do that, you end up in a bash session. And what you're gonna run in that bash session, and this is all documented in a script called prepare3 in the exercise directory, you're gonna install the content of that requirements file. So conda install, no update depth for what matters, -y to avoid asking for confirmation. And then you're telling conda, use the list of requirements in this file, right? So bear in mind what you're seeing in the screen is the content of a script. So if you run this prepare3 script from the cloned repo and the corresponding exercise directory, you're gonna do all of this. Now I'm just commenting line by line. After the installation is done, remember this is a kind of a dry run. We are doing that so that we can then later get the information of the full list of requirements for astropy, which is what we actually want. So after we run that, we use conda and export to save the list of installed packages in a file. And we're calling that file environment blah blah .yaml. Now, let me show you this output file because there is a copy in the exercise directory, because there is a little caveat here. So when you do conda and export, what you get is actually a bit more than what you need. So you have the name of the active environment at the time of installation, which was the base environment, the channels, and the dependencies. And actually, if you scroll to the end, also the prefix of the conda installation. Actually, this is done because this allows to create you a full new environment in conda with all of this. But what we need here is actually just the dependency list. So in my script, in that prepare script, there is a bit of sed being performed, these 3 commands, just to get rid of all that we don't need in this file. So basically, we are cleaning up everything. We are only keeping the list of dependencies. And you can see the end result of that sed list of commands here. Here we go. No more prefix, no more channels, no more dependency header, no more dashed list of dependencies, just the playlist of dependencies with the versions. That's what we want. And we achieved that with a dry run by opening an interactive session. We didn't do that for real. We just read it through here, right? But what we are required to do is to start an interactive session of your base image, run the conda install you desire, and save the final list of packages with conda and export. Clean it up with sed, and then you end up with what you actually want in the final Dockerfile. So the final Dockerfile specifies the name of the requirements file that you want, adds it in the container image with the add instruction, and then uses it in the conda command. So here the run instruction has conda install -y -- file requirements YAML. That way, you're installing exactly what you want. And then, please, no deps. So similar to pip, you're telling conda, just stick to the list of packages that are in that file. Do not install anything else. Again, in theory, this would be risky because you might end up with a broken environment. But because we generated this list from a real dry run conda installation, that list is not broken, unless there was a bug in the conda algorithm. And that's it. So another thing that I like here is that not only you are specifying the versions of the dependencies for your final application, astropy in this case, but you are also avoiding the unwanted update of conda, which was happening in the previous iteration of Dockerfile. Because here, because if you have a look at the requirements file, the conda version is there as well. So you are really freezing the full environment to what it was in the moment you ran the dry run. So here you achieve, again, full build reproducibility with conda installation. Welcome back, Anne.
Thank you.
And let me show you and convince you that the requirements list has also got the conda version, right? So we are really freezing everything in here. So we are running a bit late. So not to worry. I'm just adding one more comment on conda. Then we're going to have a break. And then we're going to finish off the last bit of this hands-on. So we'll be a bit late with your pipelines, but we have the entire time tomorrow to get through that. So I believe we're fine, even if we are a bit late. One more comment with conda. So there is an extra complication compared to pip. So pip installations are typically restricted to Python packages, and they're kind of self-contained in that you're really just installing some Python stuff. We are not doing anything else. Conda is a bit more invasive, and in that regard, in that it's able to also install system packages, which is a good thing. But because of that, sometimes, depending on the package you install, conda will also set up new environment variables in your installation. And in general, conda modifies your shell environment much more than pip does. And that's why if you're not in a container, you normally have a conda setup sourcing command in your Bash C. And if you use a conda environment, you will use conda activate, and that will edit some shell variables to add prefixes here and there, paths here and there, and even new variables. Turns out that conda activate is a bit hard to make work in a container context. That's because, I mean, you could run conda activate in a run instruction, but the context of that conda activate will be only within that layer. So at runtime, it will be lost. It's a bit harsh. I won't run an example in the interest of time, but that's what happens. If you run a conda activate in a run instruction, it won't stick. It will be ineffective. So you might think of embedding any sourcing commands you need in a Bash C in your home, or better in a system-wide directory. So for first, the home path is very unsafe because when you run with Docker, that would correspond to the root home directory. But then when you run with Singularity at production, the new home will be the host user home. So whatever Bash C you save in the Dockerfile won't be found when you actually run the container. So that's why you might want to stick with a system-wide sourceable file in the etc profile D directory. So in case you don't know, any bash script you add in that directory will be executed when you log in and you start the bash session. Sounds good, but when you run a Python command from a container, you are not starting a bash session. So those scripts will be ignored. So I've also seen online tutorials recommending that. I tried it myself. It does not work. So that's not the solution. It's not robust. It might work when you test it because you are opening an interactive bash shell, but it's not robust. When you run, when you do singularity exec, image name, Python, blah, blah, that's ignored. And then you break your conda environment. So honestly, the best way I can recommend to get your conda environment the way it should be is to spend some time and define the environment variables you need in the Dockerfile explicitly and manually. It's a bit tedious, but that's the most robust way. And let's have a quick look at the mini conda Dockerfile, and you will see that part of the job is done there. This is the, I just opened the link that I put in the materials. So this is the Dockerfile for mini conda 3. It's based on Debian Buster again. First thing it does, it adds the conda binary path to the path. And that's essential. That way you can find the conda commands when we are building the conda container. But because we're using the base environment, that's also where the application binaries will end up being. So that's quite good. That will make things work. It's the only variable that is being set, and actually this is actually the most important in the conda installation. The rest it is doing is just downloading conda and configuring it. My suggestion, just to be safe, I don't have enough hands-on conda experience to be aware of a case where you really need that, but it doesn't hurt. What I would suggest is to also set in your conda Dockerfile, and this is just an elaboration of the ones we saw before for astropy. Also set the conda prefix. It doesn't break anything. It would be there in a real conda installation, so just set it. Conda prefix equal to opt conda. It just makes the container more robust. So this is just to ensure the basic conda environment is working. But I'm also showing you an extra bit that you should always do when you prepare and develop conda containers. It's not required for astropy, but it might be for other packages. So when you are in that stage, when we go for the dry run, so you just start an interactive session of your base image. Well, before you run the dry run installation from the requirements file, save your environment in a file. So env will just, let me show you in the terminal. You do env, just get the list of variables that are defined in your Linux shell environment. Do it before the installation. Then you proceed with your dry run installation in the container, and then do env again after, and again save it in a file. And finally, have a look at the difference between the two environments. If most of the cases there will be nothing, the difference file, I mean, there will be no difference between the two, but there might be occasions where some new variables are being set up by the conda installation. And then you might want to review, some of those variables might be silly and you will realize you don't need them in the Dockerfile, but some of them might be crucial for the container to run. So go for this additional step of reviewing the environment of your bash shell before and after the conda installation. Record the differences and embed the relevant one in the Dockerfile. I think I needed that when I was playing with MPI for Pi or H5 Pi. I'm not 100% sure, but I have a vague memory of this. I think it's just a safe protocol to implement when you're designing conda containers. Okay, let's go just for a 10 minutes break. And then there will be another 20 minutes of best practices. There is one more on building, and then there is some HPC relevant stuff that I want to show you. So we've seen some best practices in using pip and conda to install packages in Docker containers. Remember, there is amongst the many takeaways, remember the one where we are running interactive session during the build development process in order to gain information on what we're doing. This is also, and so with Docker, you achieve that with Docker run -it, right? And then the bash, specifying the bash command after the base image name. This is also sometimes required to debug a failing build. And yes, so now that I think, I will get back to Pascal's comment that he made earlier on today, just to show you one little trick that actually Alexis taught me a few months back, which is actually quite interesting. Now I will just retrieve one of the builds I did earlier today. So, for instance, the P2 build with pip. So when you, why is it 320? Sorry, wrong directory. Okay, when you build the container image with Docker, you have the step, right? And as we said, each step is a layer, each step and layer comes out of a distinct instruction in the Dockerfile. When the step is completed, you get an alphanumeric ID. So now suppose that an error is happening in step 3, all right? And we need to debug it. Turns out that, as we said, that all of the previous layers that were successful are actually stored in the Docker cache. And so it means, this implies that, so suppose again, as an example, that step 3 is failing, you can retrieve the alphanumeric ID from step 2, which is just the one before, and run a container out of it. That way, you can open an interactive session to debug the process, using the same layer, the same installation that Docker is creating during the build. And this can be really extremely powerful in some occasions. It's a small thing, but it's really useful.
Especially for development. When you were having
the development stage.
You're trying to compile something from scratch. It's your own software. Something's going wrong. Normally, this is a good point. You have the basis where you should be able to build something, and then try to work from there if there's something going wrong.
So now let's move to the last examples of these build best practices. So we saw one pip only and one conda only Dockerfile. Now we want to mix things a bit. So now suppose our target is to build a container which has MPI for Pi. So MPI for Pi provides the Python interfaces to run MPI code written in Python. So it's basically an interface towards an MPI library. So to achieve that, so we might just be tempted to download prepackaged MPI installations, but we are going to discover in the next and last session why this is not a good idea. So we want to really build from source the MPI installation that is required by MPI for Pi. So this implies that in our container we need Python and pip, as we did before for MPI for Pi in our Python stack. But we need the compilers, and then we need to build MPI for Pi. So it turns out, as I mentioned before, Pawsey provides some MPI-based images, and we also have the Python-based image, so it would be great to be able to just merge them, right? So there is no automatic Docker way to do that. Also because in principle, you might have cases where the two Docker files underlying the two base images have something that clashes with each other. So, but let me show you, I think I put the link somewhere here. Here we go. So we have the Python Dockerfile and the Pawsey and Peach Dockerfile. Just trust me that there is no clash in this case. So if you have a look at the full list of commands, there's nothing that really can't be done together with the list of commands in the other one. So let me just show you that there's 150 lines worth of Dockerfile to build the Python-based image. And then in the case of MPI, actually things are a bit easier. So this is, I think, it's a 60 lines Dockerfile, but actually you only need the first 40 because the second bit is just about installing some benchmark suites that we don't need at production with for MPI for Pi in Python. So basically what we really need is just the first bit, which takes a Ubuntu-based image, installs compilers and build tools, and then downloads and compiles the MPI library, okay? So I would just say either ways, and note that the Python image is based on Debian, and the Pawsey MPI one is based on Ubuntu. So it means that good chances are is that if we just try and copy paste one bunch of commands, knowing that they are compatible with the other commands in terms of what it gets installed, we just copy paste, hopefully it should work. Pascal knows of cases where that doesn't happen because the two operating systems might have a different, say, list of apt installable software and so on. So it won't always work.
Especially if you're doing specific versions. So that's
here we go.
Right. So you can, of course, request, let's say, I was trying with GCC 10 and that doesn't work in Debian because in the latest Ubuntu it's there, but in the Debian one it's not. It's in a different set of repositories you'd have to pull. So it's just something to remember.
Yeah, so this is, I mean, it's a good starting point to ensure that you don't have any crashing commands, and then copy paste one in the other and then see what happens. It might break, and if it does, you need to fix it and debug it. Because it's 140 lines against 40, let's just copy paste the MPI bit on top of the Python-based image. And that actually, this is what I did in the Dockerfile that is in this directory. So I'm starting from the Python Slim base image, and then the following is just actually the copy paste of the Pawsey and pitch.
Just to
Dockerfile,
Marco, the idea would be that the Python Slim is not optimized, but it's perfectly fine to use, and that's the main difference between using the one where you compile Python specifically for the Pawsey machines, because now it's actually set up to be optimized, and Python 3 Slim is just work perfectly well, it just won't be as fast.
Yeah, I mean, yeah, thanks for the comment, Pascal. So when I said that the Python Slim the build is optimized, it's of course a range of compile time optimizations that need to be generic for any x86 processor. So needing to be cross-compatible, it won't squeeze every flop from the latest CPU architecture. But this is a kind of a trade-off that you need to accept right now when you deal with container, right? You accept that you are not optimizing for the machine you're running on, otherwise you would lose portability, and so it's not a portable container anymore. As we are on this, I mean, I was attending a container workshop at the last virtual supercomputing conference that used to be in Europe, ISC, and there was an entire 1-hour session on how to agree on how to make container deployments portable and performant on every architecture, and there was no agreement. Honestly, there was even little clue on how to get there. So right now in the container world, having CPU microarchitecture optimized containers basically means you need to build distinct containers if you really want an as well optimized or a Cascade Lake optimized, but it kind of defeats the purpose right now. So there are other ways to achieve that in an automated, usable and doable way, but it's out of scope here. If you're curious, we can get back to that later. So yeah, as Pascal points out, this Python image is as optimized as it can be to be compatible with any x86 architecture. So this is what brings Python and pip in our image, but we also need compilers, as we said, and we use the compilers to build an MPI library from source. As you see here, I'm using the best practice of creating a temporary build directory for mpitch. I'm specifying the installation prefix to be under /usr. So when make install happens, all of the relevant compiled libraries and binaries will go there. and we can remove the temporary build installation directory just to save some space. And in this case, actually, I think it saves about 200 megabytes out of a final 500 megabytes image, so quite a lot, about 30–40%. You also see that I'm using explicit versioning for mpitch, because that's one key component of this container image. Once we have mpitch in the image, we can proceed with installing MPI for Pi. I did my dry run with pip tools. Actually, we can do it again now. And you will discover sorry. I need to create a file, MPI rec, just to show you. It compile MPI rec.in, and MPI for Pi has no dependencies in pip. It's a single package, and so that's why I'm not using the requirements file at all in the Dockerfile. I'm just specifying the version and pip installing it. Remember, no cache dir to save some space, and no deps, just to ensure that we are getting this full reproducibility. Every now and then you can check with pip tools or up dry run to see that there are no new dependencies for MPI for Pi. But for this version, we know that this is all we need, okay? Well, that's it. So this is just a very simple example of how you can build a container which doesn't just pip install something, but it has something more. So it ends up being a sequence of run commands and eventually some variable definitions that get you there to the final point that you need to be.
I just want to emphasize that this is actually a very good example as well of doing commands grouped together to essentially do a specific block of installs, right? So you've got your default set, then you've got your MPI. So if you ever needed to debug this or go back to another image, right? You would normally say, oh, there's a base image in Docker that I want to start from to then go on and do something else.
Yeah. So this is a good benefit for exploiting layer caching.
Yeah.
It also maximizes the size, optimizes the size of the image, because yeah, it's 3 run commands, but they're completely independent. In that this one just deals with apt downloads and installations. This is a build from source that you are running yourself, and this is a pip installation. So there's quite little chance, if no chance at all, that these 3 blocks edits one other file. So this is really quite optimized, still quite readable with this block structure without making the image size grow too much. Let's skip the build, just in the, actually, let's build it under the hood as we do other things. MPI, let's call it M1. When the Dockerfile name is just Dockerfile, you can skip this specification. And here we go. And this brings us, so I'm going to reuse this MPI for Pi example quite soon.